somewhere beneath your feet, the ground is not as solid as it seems. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. Right now, under roughly 15% of the Earth's land surface, water is slowly eating the rock away. Quietly, patiently, one drop at a time. Picture the Earth from high above. You can see the brown and gold of deserts, the deep green of forests, the white crowns of mountain ranges. But there is something you cannot see from up there. There are places on this planet where the ground itself is hollow, where vast rooms and tunnels and rivers exist in total darkness, carved into the rock over millions of years. And sometimes, without warning, the ceiling of that hidden world gives way. The ground opens up. This is the world of Sinkholes and Karst Landscapes. Karst is the name scientists give to land shaped by dissolving rock. The word comes from a region in Slovenia, a small country in Central Europe, where this kind of terrain was first studied closely. The Karst Plateau there is a rocky, dramatic place, full of strange formations and hidden caves. Scientists borrowed its name and used it for all landscapes like it, all over the world. Karst landscapes cover an enormous portion of our planet. About 20% of the Earth's ice-free land surface sits on rock that can dissolve. That is an area larger than the entire continent of South America. Beneath that land, water has been carving passages and chambers for millions of years, building a hidden architecture that most people will never see. The rock that makes this possible is usually limestone. Limestone is a pale, soft-looking rock made mostly from the shells and bones of ancient sea creatures. When those creatures died hundreds of millions of years ago, they sank to the ocean floor. Layer by layer, their remains compressed into stone. Over time, the sea retreated. The land rose, and those ancient seafloors became the hills and plains we walk on today. There is something quietly astonishing about that. The ground beneath a farmer's field in Kentucky or a city street in Florida was once the floor of a warm, shallow sea. The rock underfoot is made of creatures that lived before the dinosaurs. And that same rock, so old and so dense, is slowly being dissolved by something as gentle as rainwater. Rainwater is slightly acidic, not dangerously so, but enough. As rain falls through the air, it picks up a small amount of carbon dioxide and forms a weak acid called carbonic acid. When that water seeps into the ground and touches limestone, a slow chemical reaction begins. The acid dissolves the rock, not quickly, not dramatically. Over thousands and millions of years, it carves tiny cracks into wide passages, and wide passages into vast caves. And then one day, the roof of one of those caves becomes too thin to hold what is above it. The soil, the road, the house, the tree, and it falls. Sinkholes can open in seconds. There are videos of roads simply vanishing, of cars dropping into sudden holes, of entire buildings tilting into the earth. In 2013, a man in Florida was swallowed by a sinkhole that opened beneath his bedroom while he slept. The ground gave way in the night silently, and he was gone. It is one of the most unsettling things the earth can do. But sinkholes are not random acts of chaos. They are the visible result of a process that has been running deep and slow for an almost unimaginable length of time. Every sinkhole tells a story. It is the final chapter of a story that began with rain falling on stone, perhaps 1,000,000 years ago. And that story is connected to everything. The caves that form beneath karst landscapes hold some of the most important freshwater reserves on Earth. They shelter creatures found nowhere else. They preserve fossils and ancient artifacts. They shape the rivers above them and the springs that feed them. The hidden world below is not separate from the world above. It supports it. This episode is about that hidden world. It is about the slow, patient power of water. It is about the ground beneath your feet and the remarkable, fragile, ancient system that lies just below the surface. There are 101 facts waiting for you here, each one a small window into a world most people never think about. So settle in. Close your eyes if you like, and let the earth show you what is underneath. Karst is a type of landscape. That is the simplest way to say it. It is land shaped not by wind or by ice, but by water slowly eating through rock from the inside out. The word itself comes from a region in Slovenia, a small country in Central Europe, where this kind of terrain was first studied closely by scientists. That region is called the Kras Plateau. And when European geologists began mapping it in the 1800s, they borrowed its name to describe every landscape like it anywhere on Earth. So when scientists say karst, they mean any place where the ground beneath the surface is being slowly dissolved by water. The rock is not being crushed or pushed. It is being eaten quietly over thousands and thousands of years. Not every kind of rock dissolves this way. Granite, for example, is tough. Sandstone holds its shape, but certain rocks are different. Limestone is the most common of these. Limestone is a pale, often cream-colored rock made mostly of calcium carbonate, the same mineral found in seashells and coral. Dolomite is another, very similar to limestone in its makeup. Gypsum is softer, almost chalky, and dissolves even faster. These are the rocks that karst is built from. They are the rocks that water can slowly take apart, grain by grain, over deep stretches of time. Karst landscapes cover an enormous portion of our planet. Scientists estimate that roughly 15 to 20% of the Earth's ice-free land surface is karst or contains karst features. That is an area close to 10 million square miles. To picture that, imagine the entire continent of Africa, and then add all of Australia on top of it. That is roughly the size of the world's karst regions combined. It is not a rare or unusual thing. It is one of the most common landscape types on Earth. These regions are found on every continent. China has some of the most dramatic karst scenery in the world, with tall limestone towers rising from green valleys in places like Guilin and Zhangjiajie. The Yucatan Peninsula in Mexico sits almost entirely on a flat sheet of karst limestone, with no rivers running on the surface at all. The water there moves entirely underground. The Caribbean islands, large parts of the American Southeast, the hills of Kentucky and Tennessee, the mountains of Slovenia and Croatia, the deserts of the Middle East, the plains of Russia. Karst hides beneath all of these places and many more. What makes karst so easy to overlook is that much of it is invisible from the surface. You can walk across a karst landscape and see only gentle hills, thin soil, and scattered rock. The ground beneath your feet might look perfectly solid, but below that surface, the rock could be riddled with tunnels and chambers, some no wider than a finger, others large enough to hold a cathedral. The rock looks whole. It is not. Limestone, the most common karst rock, forms in a very specific way. Most of it was made at the bottom of ancient seas. Tiny sea creatures, corals and shellfish, and microscopic organisms built their shells and skeletons from calcium carbonate pulled out of the seawater. When they died, they sank. Over millions of years, their remains piled up in thick layers on the seafloor. Pressure and time compressed those layers into solid rock. This means that much of the limestone we walk on today was once alive. It was once a reef, a seafloor, a shallow tropical sea teeming with creatures. Some of the limestone beneath the American Midwest formed during the Ordovician period, roughly 450 million years ago, when shallow seas covered the center of the continent. The rock under your feet in parts of Indiana or Ohio is older than the dinosaurs by a factor of 2. That age matters. It tells us that karst is not a new thing. It is not something that started recently. These landscapes have been forming and reforming across hundreds of millions of years. The karst regions we see today are just the current chapter of a process that has been running since long before any human being existed to notice it, and the rock is still dissolving. Right now, tonight, in the dark beneath the surface, water is moving through tiny cracks in limestone all over the world. It is widening those cracks, grain by grain, drop by drop. The process is too slow to see, but it is happening. It never stops. The ground is patient in a way that nothing living can quite be. And it has been at this work for a very long time. The agent of all this slow destruction is something remarkably ordinary. It is rain, not acid rain, not some rare chemical from deep inside the earth. Just ordinary rainwater falling from clouds the way it has fallen for billions of years. But rainwater carries a secret. As it falls through the air, the same gas that living things breathe out. That carbon dioxide dissolves into the water and forms a weak acid called carbonic acid. The change is subtle. You could drink it and barely notice. But to limestone, it matters enormously. Carbonic acid reacts with the calcium carbonate in limestone and slowly breaks it apart. The rock does not melt like ice. It dissolves, molecule by molecule, the way sugar disappears into warm water. The dissolved minerals get carried away by the moving water, grain by grain, leaving behind a little more empty space than there was before. This process has a name: chemical weathering. And it is the engine that drives everything in karst country. It begins the moment rain touches the surface. Water pools in the tiniest, low spots on exposed limestone. It finds the hairline cracks, the places where two layers of rock meet, the spots where ancient pressure fractured the stone. It seeps in. It starts to work. A crack that was a fraction of a millimeter wide becomes slightly wider, then wider still. Over thousands of years, a crack becomes a channel. A channel becomes a passage. A passage becomes a cave. The speed of this process depends on a few things. Warmer water dissolves limestone faster than cold water. Water that has moved through soil picks up extra carbon dioxide from decaying plant roots and becomes slightly more acidic, slightly more powerful. This is why karst landscapes often develop most dramatically in warm, wet climates. Places like the tropics, where rain is heavy and vegetation is thick, and the soil is alive with biological activity. The karst towers of southern China, those tall green peaks rising from flat plains, formed in exactly these conditions. Warm, wet, rich with life above and below. But even in cooler places, the process continues. In the limestone hills of England, in the karst plateaus of Slovenia, in the cave country of Kentucky, the water is still doing its quiet work. It is slower in the cold, but it does not stop. There is something worth pausing on here. The water does not know what it is doing. There is no intention in a raindrop, no plan, no goal. And yet, over time, water acting on rock produces some of the most complex and beautiful underground structures on Earth. Vast cave systems with rooms sometimes the size of cathedrals. Underground rivers that run for miles without ever seeing sunlight. Towers and arches and sinkholes and springs, all carved by the same simple chemistry, repeated endlessly across deep time. Scientists estimate that limestone dissolves at a rate of roughly 20 to 100 millimeters per 1,000 years, depending on the climate and the chemistry of the water. That sounds almost impossibly slow, but multiply that rate across 1,000,000 years or 10 million years, and you begin to understand how the great karst landscapes of the world came to be. The caves of Carlsbad Caverns in New Mexico took millions of years to form. The cave systems of the Yucatan Peninsula in Mexico, those vast flooded passages beneath the jungle floor, have been developing for hundreds of thousands of years. Water also works from above and below at the same time. Rain dissolves the surface. Groundwater, the water that fills the spaces between rock grains deep underground, dissolves from within. The rock is being eaten from every direction at once. The surface slowly lowers. The underground spaces slowly grow. The two processes move toward each other across geological time, and eventually they meet. That meeting is when things get dramatic. When the ceiling of an underground space grows thin enough, when the rock above has been weakened by water long enough, the surface can no longer hold. It gives way. A sinkhole opens. The ground that looked solid from above was never quite as solid as it seemed. But that moment of collapse is not the beginning of the story. It is the end of a very long one. The real story started with a single raindrop carrying a little dissolved carbon dioxide, finding a crack in a piece of ancient rock. Everything that follows, every cave, every underground river, every sudden hole in the earth traces back to that quiet, unhurried beginning. The rain falls, the rock listens, and the ground slowly begins to change. To understand how a sinkhole is truly born, you have to go back further than the rain. You have to go back further than the rock itself. You have to go back to the beginning of everything. The limestone that dissolves so easily in rainwater is made mostly of calcium carbonate. That is a compound built from calcium, carbon, and oxygen. These These are not rare or unusual elements. They are among the most common building blocks in the known universe. Carbon was forged inside ancient stars billions of years before our sun ever existed. When those stars died, they scattered their contents across space. That carbon drifted through the dark for a long time. Eventually, it became part of the cloud of gas and dust that collapsed to form our solar system. It became part of Earth. It became part of you. The calcium in limestone has a similar story. It too was made in the hearts of massive stars. It too was scattered by stellar explosions called supernovae. When you look at a pale cliff of limestone, you are looking at material that was cooked inside a star that no longer exists. The rock feels solid and permanent, but it is made of something ancient and traveled. The oxygen in calcium carbonate has its own path. Much of Earth's oxygen was not here at the very beginning. Early Earth had almost no free oxygen in its atmosphere. Then, around 2.5 billion years ago, tiny living things called cyanobacteria began releasing oxygen as a byproduct of using sunlight for energy. They changed the entire atmosphere of the planet. That oxygen bonded with carbon and calcium over deep time, building the very mineral that sinkholes need to form. Life itself helped create the conditions for limestone to exist, and the water that does the dissolving carries its own remarkable origin. Scientists believe that much of Earth's water arrived from space. Comets and water-rich asteroids bombarded the young Earth for hundreds of millions of years. They delivered ice and water vapor from the cold outer edges of the solar system. That ancient delivery is still here. It fills the oceans. It falls as rain. It seeps into the ground. The water that is quietly dissolving a limestone cave somewhere beneath your feet right now may have traveled from the outer solar system to reach this planet billions of years ago. So when a sinkhole forms, it is not just a geological event. It is the end point of a process that stretches across cosmic time. Stardust became rock. Cometary ice became water. Ancient bacteria changed the air. Rain formed, and the rain, carrying dissolved carbon dioxide, began its slow and patient work on the rock below. The actual mineral being dissolved is called calcite. Calcite is the crystalline form of calcium carbonate, and it is beautiful up close. It forms clear or white crystals with a soft, glassy shine. Under the right light, calcite splits light into two beams, a property called double refraction. A single crystal of calcite can make you see two images of whatever lies beneath it. Limestone is made of countless tiny calcite crystals pressed together over millions of years under the weight of ancient seas. Those ancient seas matter. Most limestone was not made on dry land. It formed on the floors of warm, shallow oceans, the shells and skeletons of sea creatures, tiny organisms called foraminifera, corals, mollusks, and others, piled up on the seafloor over millions of years. Their calcium carbonate remains compressed into solid rock. When you find limestone in the middle of a continent, far from any ocean, that land was once underwater. The rock remembers a sea that is long gone. Over time, those ancient seabeds were lifted by the slow movement of tectonic plates, the great slabs of rock that carry the continents. They rose above sea level. Rain began to fall on them, and the dissolving began. The calcite crystals that once formed the shells of sea creatures started to break apart, molecule by molecule, carried away in water that was barely acidic at all. This is the quiet miracle at the heart of every sinkhole. The rock is not smashed or torn. It is gently, chemically persuaded to let go. Calcium and carbonate ions slip into solution and are carried away by moving water. The space they leave behind is invisible at first, just a slightly wider crack, just a slightly larger gap between grains of rock. But the water keeps coming. The rain keeps falling. And the space keeps growing, one dissolved crystal at a time, deep in the dark, beneath the surface of the earth. That space keeps growing, and eventually the ground above it must respond. Geologists have studied sinkholes for well over a century, and what they have found is that not all sinkholes form the same way. There are 4 distinct types. Each one is shaped by a different set of forces. Each one tells a slightly different story about what is happening in the rock below. understanding them helps us see the ground beneath our feet not as something fixed and permanent, but as something that is always quietly in motion. The first type is called a dissolution sinkhole. It is the slowest and in many ways the gentlest of the four. In a dissolution sinkhole, the limestone sits very close to the surface with little or no soil covering it. Rainwater flows directly across the rock. It seeps into every crack and joint. Over hundreds or thousands of years, the rock dissolves away in a broad, shallow bowl shape. The surface sinks gradually, almost imperceptibly. There is no sudden collapse. The land simply lowers itself like a slow exhale. These sinkholes often fill with water and become ponds or wetlands. They are common in places like Florida and the Yucatan Peninsula, where the limestone is close to the surface and rainfall is plentiful. From above, they look like gentle depressions in the earth, soft-edged and quiet. The second type is called a cover subsidence sinkhole. Here, a layer of loose sediment, sand or clay or soil, sits on top of the dissolving limestone below. As the rock dissolves and small cavities form, the loose material above slowly filters down into the gaps. It moves grain by grain, like sand through the neck of an hourglass. The surface above sinks steadily, but slowly enough that it rarely causes alarm. These sinkholes can take decades to become visible. They tend to be small, often just a meter or two across. But they are a sign that something larger may be happening below. The sediment is filling the void for now, but voids have limits. The third type is the one that makes headlines. It is called a cover collapse sinkhole, and it is the sudden, dramatic kind that swallows cars and splits roads open overnight. In a cover collapse sinkhole, the limestone below has dissolved into a large open cavity. The soil and sediment above it form a kind of roof, held up by nothing but its own cohesion and the friction of its edges. For a long time, that roof holds. Water seeps through it slowly. The cavity below grows. The roof thins. And then, when the weight above finally exceeds what the weakened ground can support, the surface gives way all at once. The collapse can happen in seconds. A circular hole opens in the earth with steep, nearly vertical walls. sometimes dropping 10, 20, or 30 meters straight down. The speed of it is what makes these sinkholes so dangerous. There is almost no warning visible from above. The ground looks solid right up until the moment it is not. The fourth type is called a subocean sinkhole, and it works through a process that is almost like the earth eating itself from the inside. In subocean, water moving underground carries fine particles of soil and sediment along with it, washing them away through cracks in the rock below. This process is called piping, and it creates hollow channels within the soil itself, not just in the rock. Over time, the soil structure weakens. The surface begins to sag and crack in irregular patterns. Subocean sinkholes tend to have uneven, ragged edges rather than the clean circular shape of a collapsed sinkhole. They are common in areas where the soil is sandy or silty and where underground water flow is strong. What is remarkable is that all four of these types, so different in their speed and their shape and their drama, share the same root cause: water moving through rock, carrying dissolved minerals away. The forces at work are not violent. There is no explosion, no earthquake, no sudden rupture. There is only the patient, persistent chemistry of slightly acidic water meeting calcium carbonate rock, repeated billions of times over thousands of years. Gravity pulls the water downward. Pressure from the weight of the earth above squeezes it through the narrowest cracks. The weak acid in the water does its slow chemical work, and the rock, grain by grain and crystal by crystal, yields. The void grows. The surface above it waits, unknowing. And the four kinds of sinkholes are simply four different ways that the surface eventually learns what has been happening below it all along. Of all four types, the cover collapse sinkhole is the one that captures our imagination most completely. It is the sudden kind, the dramatic kind, the one that swallows a car or a yard or a corner of a road in what feels like an instant. But even this sudden event is not truly sudden. It is the final moment of a very long story. To understand the scale of what happens, picture a swimming pool buried beneath a quiet neighborhood street, not a small backyard pool. A full competition pool 50 meters long, holding nearly 2 million liters of water. Now imagine that pool is not filled with water, but with empty air, a hollow space, hidden in the rock or soil below the surface, unseen and unfelt by anyone walking above it. That hollow space has been growing for decades, perhaps centuries. The ceiling of that space is a thin layer of soil and clay, held together by its own weight and by the roots of grass and trees above it. For a long time, that ceiling holds, and then one day it does not. The collapse itself can happen in seconds. A cover collapse sinkhole can open to its full width almost instantly, dropping everything on the surface straight down into the void below. The largest cover collapse sinkholes on record have measured more than 300 meters across. That is wider than 3 American football fields laid end to end. Some have dropped more than 100 meters deep. That is roughly the height of a 30-story building, straight down into the earth. The Winter Park Sinkhole in Florida, which opened in May of 1981, is one of the most studied cover collapse events in recorded history. It began with a small depression in a yard. Within hours, it had swallowed a house, part of a road, several cars, and a public swimming pool. By the time it stopped growing, it was more than 100 meters wide and 30 meters deep. The entire event, from first crack to final collapse, took less than 3 days. Scientists who arrived to study it found that the void below had been forming for years before the surface gave way. What makes cover collapse sinkholes so hard to predict is the very thing that hides them: the cover layer, that thin skin of soil and clay sitting above the void, can remain intact and stable for an extraordinarily long time. It holds its shape the way a thin crust of ice holds over a pond in early winter. From above, the surface looks solid. It feels solid underfoot. There is no visible sign of what waits below. Then a heavy rain saturates the soil, adding weight, or a drought dries it out, removing the moisture that gave it cohesion. Or a water main breaks underground, washing the soil away from below, and the crust fails. The weight involved is staggering. A single cubic meter of wet soil weighs roughly 1,600 kilograms. That is heavier than a small car. When a sinkhole opens, the surface above it can be holding thousands of cubic meters of that material, all of it pressing down on a ceiling of rock or clay that has been slowly hollowed from beneath. When the ceiling finally gives, all of that weight drops at once, free falling into the void below. The sound of a large cover collapse sinkhole has been described by witnesses as a deep, hollow boom, followed by a rushing sound, like a waterfall of earth and debris pouring into a dark room. In Florida alone, cover collapse sinkholes cause an estimated $300 million in property damage every year. The state sits on a thick layer of limestone that has been dissolving for millions of years. The aquifer below, the vast underground reservoir that Floridians depend on for drinking water, is riddled with caves and channels carved by that same slow chemistry. The surface above it is, in many places, a thin and aging ceiling over a world of hollow spaces. And yet, even knowing this, it is hard not to feel a quiet sense of wonder at the scale of what is happening. Beneath ordinary streets and lawns and parking lots, the rock is doing what it has always done. Water is moving through it. Minerals are dissolving. Spaces are opening. The surface above carries on, unaware, the way we all carry on above the deep and patient processes that shape the world we live on. The void grows in the dark. The surface waits, and the gap between those two worlds, between what we can see and what is quietly happening below, is sometimes only as thick as the ceiling of a buried room. Sometimes that ceiling gives way in places the whole world notices. In 2010, a sinkhole opened in Guatemala City that stopped people in their tracks. It appeared almost overnight, a near-perfect circle punched into the middle of a dense urban neighborhood. The hole was roughly 60 feet wide and about 300 feet deep. It swallowed a 3-story building hole. Standing at the edge, witnesses described looking down into what seemed like a perfectly drilled shaft. The walls almost smooth, dropping straight into darkness far below. The city around it carried on its ordinary morning traffic and noise and the smell of rain. And there, in the middle of it all, was this impossible vertical wound in the earth. scientists noted that the Guatemala City sinkhole was not carved by dissolving limestone in the traditional sense. The ground beneath the city is made largely of a loose volcanic material called pumice, which erodes quickly when water moves through it. Pipes had been leaking for years. The water did its quiet work, and then the surface gave way all at once. That sinkhole became one of the most photographed geological events of its decade. The image of it is striking in a way that is hard to explain. It looks less like something that happened and more like something that was always there, hidden just beneath the pavement, waiting. A very different kind of famous sinkhole sits in the desert country of Turkmenistan in Central Asia. It is called the Darvaza gas crater, though most people simply call it the door to hell. It is not a karst sinkhole in the geological sense, but it shows what can happen when the ground collapses over an underground void. In 1971, Soviet engineers drilling for natural gas accidentally broke through into a large underground cavern. The ground collapsed, opening a crater roughly 230 feet wide. Fearing that poisonous gas would spread, the engineers set the crater on fire, expecting it to burn out in a few weeks. It has been burning ever since. At night, the orange glow of it lights the surrounding desert in a warm, flickering halo. From a distance, it looks like a campfire left burning on the floor of the earth. Up close, the heat is intense, and the roar of the flames is constant. It is one of the strangest sights on the planet's surface. Back in the world of true karst, one of the most celebrated sinkholes on Earth sits not in a city, but in the ocean. The Great Blue Hole, off the coast of Belize in the Caribbean Sea, is a marine sinkhole roughly 1,000 feet across and about 400 feet deep. From above, it is a deep circle of midnight blue, surrounded by the pale turquoise of shallow reef water. The contrast in color is extraordinary. The dark center seems to absorb light rather than reflect it. Pilots flying over the coast of Belize can spot it easily from altitude. A dark eye set into the bright sea. Jacques Cousteau, the famous ocean explorer, named it one of the top diving sites in the world in 1971. The walls of the Great Blue Hole are lined with ancient stalactites, the long stone formations that hang from cave ceilings, which tells scientists that this place was once a dry cave system. Sea levels were much lower during the last ice age, roughly 15,000 years ago, when the ice melted and the seas rose. The cave flooded and the roof eventually collapsed, leaving this vast circular window open to the sky. In the United States, one of the most dramatic karst depressions is not a sudden collapse, but a gradual one. The Macungie Sinkhole in Pennsylvania, the Golly Hole in Alabama, and the Winter Park Sinkhole in Florida have each, at different times, drawn crowds of stunned onlookers. The Winter Park Sinkhole of 1981 opened gradually over the course of a day, eventually swallowing a house, part of a road, several cars, and a municipal swimming pool. It grew to about 350 feet wide. Residents stood at the edge and watched their neighborhood disappear in slow motion, the ground peeling back like the skin of something being opened from below. What all of these places share across continents and climates and centuries is that moment of revelation. The surface, which we trust completely, which we build on and walk on and plant gardens on, turns out to have been resting on something less solid than we imagined. The ground we stand on is not the bottom of the world. It is, in many places, just the top of something much deeper and much older and much more quietly active than anything we can see. Beneath that surface, beneath the soil and the roots and the bedrock we can touch, there is another world entirely. It does not announce itself. It has no sky. It has no sunlight, but it has rivers. In karst regions, water does not only move above ground, it moves below it, sometimes for miles and miles, through passages and tunnels carved by the same slow chemistry that creates sinkholes. These are called underground rivers, and they are exactly what they sound like. Real rivers, moving water, flowing through the dark. The process that creates them begins the same way it always does in karst country. Rainwater picks up carbon dioxide from the air and the soil, turning faintly acidic. Then it finds a crack in the limestone. It widens that crack over thousands of years, and eventually the crack becomes a passage. The passage becomes a tunnel. The tunnel becomes something large enough for water to pour through freely, rushing and churning in the total darkness below the earth. Some of these underground rivers are enormous. The Puerto Princesa subterranean river in the Philippines runs for more than 5 miles through a cave system before it empties directly into the sea. Boats can travel on it. The cave ceiling above it rises in some places to nearly 200 feet, like the inside of a cathedral, with no light and no sound except the echo of moving water. It is one of the longest navigable underground rivers on Earth, and it sits in a region of dramatic karst limestone that rises from the jungle in tall, rounded peaks. In Mexico, the Yucatan Peninsula holds one of the most complex underground river systems ever mapped. The water there moves through a vast web of flooded tunnels called an ankyline system, meaning the tunnels connect both to fresh groundwater and to the sea. Divers have explored these passages for decades, and the maps they have made stretch for hundreds of miles. The Sistema Sac Acton, one of the longest known underwater cave systems in the world, runs for more than 200 miles through the limestone beneath the jungle floor. And scientists believe there is still much more of it left to find. What makes underground rivers so remarkable is not just their size. It is their speed. Water moving through open limestone passages can travel much faster than water filtering slowly through soil or porous rock. In some karst systems, dye tests have shown that water can move from a sinkhole on the surface to a spring several miles away in just a matter of hours. The water does not seep. It flows. It rushes. It behaves like a river because it is one, just hidden from view. This speed matters for a quiet and serious reason. Because the water moves so fast through open passages, it does not get filtered the way groundwater normally does. In most places, water moving through soil and rock gets cleaned slowly, with particles and bacteria and pollutants caught and held by the earth. But in karst, the water skips that process. What goes into a sinkhole can come out of a spring miles away in nearly the same condition it went in. This makes karst aquifers, the underground water supplies that millions of people drink from, both incredibly incredibly valuable and unusually fragile. An aquifer is simply a layer of rock or sediment that holds water underground, like a sponge the size of a county. Karst aquifers are different from most because they are not sponges at all. They are more like plumbing, open pipes, fast-moving channels. The Floridan aquifer, which sits beneath much of Florida and parts of Georgia and South Carolina, is one of the most productive karst aquifers in the world. It supplies drinking water to tens of millions of people. It also feeds hundreds of natural springs, some of which push millions of gallons of crystal clear water to the surface every single day. Those springs are where the hidden rivers finally come into the light. They emerge from the base of a cliff or from a pool in the middle of a forest or from the floor of a river, bubbling up cold and clear from somewhere deep below. The water that surfaces at a Florida spring may have entered the ground miles away, weeks or months earlier, flowing the whole time through passages no human has ever seen. There is something deeply calming about that idea. Water finding its way, moving through the dark, through the rock, through the ancient carved channels of a world that has been quietly working for millions of years. It arrives at the surface cool and bright, as if it has been kept safe somewhere below, waiting for the right moment to return. That water, rising cool and clear into the light, has passed through something remarkable on its way. It has moved through caves, real caves, not just cracks or gaps, but full rooms carved into the rock, with ceilings and floors and passages that stretch for miles in every direction. Caves are where the story of karst becomes something you can walk inside. A cave forms the same way a sinkhole does, through the slow, patient work of slightly acidic water dissolving limestone over time. But where a sinkhole collapses downward, a cave grows inward. Water seeps into a crack. It widens the crack. It follows the path of least resistance, moving along joints and fractures in the rock, dissolving a little more with every pass. Over thousands of years, that crack becomes a tunnel. That tunnel becomes a passage. That passage connects to others, and slowly the rock opens up into something vast. The Mammoth Cave System in Kentucky is the longest known cave system on Earth. Scientists have mapped more than 420 miles of passages inside it. That number keeps growing. Explorers are still finding new tunnels, new rooms, new connections that no one has charted before. The cave has been forming for around 10 million years, and in all that time, the water has never stopped working. Caves breathe. That is not a poetic idea. It is a physical fact. Air moves in and out of cave entrances as the pressure outside changes with the weather. On cold days, warm air from deep inside the cave flows outward. On warm days, cool cave air is drawn back in. This slow exchange of air is one of the ways scientists know a cave system is large. If you stand at a cave entrance and feel a steady breeze coming from inside the rock, you are standing at the edge of something enormous. The temperature inside most caves stays almost perfectly constant year-round. In temperate regions, that temperature tends to hover around the average annual surface temperature of the area, usually somewhere between 50 and 60 degrees Fahrenheit. The rock insulates the cave from the seasons above. Summer heat cannot reach it. Winter cold cannot either. The cave exists in its own steady, quiet climate, unchanged, while the world outside cycles through heat and frost and heat again. This is where the rhythm of caves becomes clear. The surface world pulses with seasons. Rain falls in wet months, then slows in dry ones. Snowmelt rushes down in spring. Drought tightens the land in summer. All of that variation reaches the cave, but slowly softened by the rock. A flood on the surface might raise the water level inside a cave days, or even weeks later. A dry spell on the surface might reduce the drip of water inside a cave gradually over months. The cave does not react quickly. It absorbs the changes and smooths them out, the way a thick blanket absorbs cold. Water drips through the ceiling of a cave at a rate set by the seasons above. In wet seasons, the drip quickens. In dry seasons, it slows. This rhythm, repeated over thousands of years, is actually recorded in the cave itself. The minerals left behind by that dripping water build up in layers, like rings in a tree. Scientists can read those layers and reconstruct the climate of the past. A cave formation can hold a record of rainfall patterns going back hundreds of thousands of years, written in stone, one thin layer at a time. Caves also connect to the surface through the movement of living things. Bats roost inside caves by the millions, flying out at dusk to feed on insects and returning before dawn. Their droppings, called guano, pile up on the cave floor over centuries and become a rich source of nutrients for the creatures that live in the dark below. The bats carry the energy of the outside world into the cave with them every night. They are a living link between the surface and the deep. Some caves hold pools of perfectly still water, so clear and so calm that the reflection on the surface looks identical to the ceiling above. The water does not move. There is no wind to disturb it. The only sound is the occasional drip from somewhere far above, a single note falling into silence. Those pools can be ancient, fed by the same slow seep of groundwater that carved the cave in the first place. The water arrived over years. It will stay for years more. Everything in a cave moves on a different clock than the world above. Slower, quieter, more patient. The rock dissolves one molecule at a time. The formations grow one thin layer per year. The water waits, and the cave, in its stillness, keeps a record of everything. That drip is not just a sound. It is a builder. Each drop of water that falls from a cave ceiling carries something invisible inside it. It carries dissolved calcite, which is a mineral pulled from the limestone rock above. When that drop hits the air of the cave, something changes. A tiny bit of carbon dioxide escapes from the water. And when that happens, the calcite can no longer stay dissolved. It has to go somewhere, so it stays behind. It settles. It hardens. And over time, drop by drop, year by year, it builds something extraordinary. Stalactites grow down from the ceiling. Stalagmites grow up from the floor. Both are made of the same material, the same slow process, the same patient drip. A stalactite begins as a thin, hollow tube, no wider than a drinking straw. Scientists call these soda straw stalactites, and the name fits perfectly. Water runs through the center of the tube and deposits a thin ring of calcite at the tip with each passing drop. over decades, the tube thickens. Over centuries, it becomes the long stone icicle we recognize hanging from cave ceilings. Stalagmites form where the drops land. The water hits the floor and spreads outward, leaving behind its tiny cargo of calcite. The mound grows upward slowly, like a candle building its own wax. Some stalagmites are rounded and smooth at the top. Others are sharp and narrow. Their shape depends on how fast the water drips and how much calcite each drop carries. A fast drip spreads the mineral wide. A slow drip stacks it tall and thin. The growth rate of these formations is almost impossibly slow. Most stalactites grow about 1 centimeter every 100 years. Some grow even slower than that. A stalactite 1 meter long may have taken 10,000 years to reach that size. When you stand in a cave and look up at a ceiling draped in stone formations, you are looking at something that began growing before recorded human history. Before the first cities, before writing, the cave was building while the world above it changed completely. When a stalactite and a stalagmite finally meet, they form a single column of stone that connects floor to ceiling. These columns can be massive, as wide as a tree trunk, as tall as a house. In some caves, dozens of columns stand together in rows, and the effect is exactly what the section title suggests. It looks like the inside of a cathedral. The columns rise in silence. The ceiling arches above them. The stone glows pale white or soft orange or deep rust red, depending on what minerals have mixed into the calcite along the way. Iron gives the stone a warm amber color. Manganese turns it dark gray or black. Pure calcite is nearly white, almost luminous in lamplight. These formations are called speleothems, which simply means cave deposits. They come in more shapes than most people ever imagine. Some look like cave popcorn, small rounded knobs that cluster on walls and ceilings. Some grow in thin curved sheets called cave bacon, striped with color like layers of sediment. Some form delicate spiraling shapes called halictites, which twist in directions that seem to ignore gravity entirely. Scientists believe halictites grow that way because of tiny impurities in the water that push the calcite sideways as it forms. The cave around these formations is not passive. It is a neighbor, a partner in the process. The humidity inside the cave must stay high for the formations to grow. If the air becomes too dry, the water evaporates before it can deposit its calcite. The temperature must stay stable. Most caves hold a nearly constant temperature year-round, close to the average annual temperature of the region above. A cave in a temperate forest might stay around 10 degrees Celsius all year, cool and steady, while the world above swings from summer heat to winter frost. That stability is what makes caves such remarkable record keepers. Scientists can drill into old stalactites and read their layers like tree rings. Each layer holds chemical information about the climate at the time it formed. A thin layer might mean a dry year with little dripping water. A thick layer might mean a wet year with many drops. By reading these layers, researchers have reconstructed climate records going back hundreds of thousands of years. The stalactite does not know it is keeping records. It is simply doing what water and stone have always done together: dripping, hardening, growing, remembering. The cave holds all of this in quiet. The formations stand in the dark, growing their fraction of a millimeter, patient beyond any human measure of patience. The drip falls, the calcite stays, and the cathedral keeps rising. The cathedral stands in silence, but it is not empty. Deep inside karst caves, in places where no sunlight has ever reached, life has found a way. Not just surviving, but thriving, adapting over thousands of generations to one of the strangest environments on Earth. No light, very little food, cold, still air, and yet creatures live here. Some of them live nowhere else on the planet. Scientists have a name for animals that spend their entire lives underground. They call them troglobites, which simply means cave dwellers. These are not animals that wander in from outside. They were born underground. They will die underground. Their ancestors lived underground so long ago that their bodies have slowly changed to match the darkness. Evolution shaped them quietly over enormous stretches of time. One of the most striking changes is the loss of eyes. Many cave creatures have no working eyes at all. In a place eyes cost energy to build and maintain. Over many generations, animals that spent less energy on eyes survived a little better. Their descendants inherited smaller and smaller eyes. Eventually, the eyes disappeared almost entirely. What remains in some species is just a faint trace, a tiny patch of tissue beneath the skin, a ghost of the eye that once was. Along with their eyes, many cave animals lost their color. Pigment, the substance that gives skin and scales their color, also costs energy to produce. In a world with no sunlight and no predators that hunt by sight, color offers no advantage. So cave fish, cave shrimp, cave salamanders, and cave spiders are often pale white or faintly pink. Their blood vessels show through their translucent skin. They look almost ghostly, delicate, and strange, like creatures from another world entirely. But losing eyes and color is only part of the story. Cave animals often gain remarkable new abilities in exchange. Many develop extraordinarily sensitive lateral lines, which are tiny pressure-sensing organs along their bodies that detect the faintest movements in water. A blind cave fish can navigate a completely dark pool with precision, sensing the ripples bouncing off cave walls. It does not need to see. It feels the shape of the room around it. The ohm is one of the most extraordinary cave creatures ever discovered. It is a small, pale salamander that lives in the underground rivers of karst caves in southeastern Europe. The ohm can live for more than 100 years, making it one of the longest-lived amphibians on Earth. It can survive without food for up to 10 years by slowing its body down to an almost undetectable crawl. Its heart barely beats. Its cells barely divide. It simply waits, patient in the cold, dark water, for something to eat. The ohm is almost entirely blind, but it can sense weak electrical fields in the water around it, a rare ability that helps it detect prey. It can also sense Earth's magnetic field, which scientists believe may help it orient itself in the total darkness of its underground world. An animal with no eyes, navigating by electricity and magnetism in a flooded cave beneath a mountain. The more you learn about it, the more extraordinary it becomes. Cave crickets are another remarkable group. They live in caves around the world, often near the entrance zones where a little light still filters in. Their legs are enormously long compared to their bodies, giving them a spindly, reaching appearance. Those long legs are packed with sensory hairs that detect the tiniest vibrations in the air. A cave cricket can sense a predator approaching before it hears or sees anything at all. Some of the rarest creatures on Earth live in single cave systems and nowhere else. The Texas blind salamander, for example, lives only in a specific set of underwater caves beneath the Edwards Plateau in Texas. Its entire known world is a network of flooded limestone passages. If those caves were contaminated or drained, the species would vanish entirely. It has no other home. It has never needed one. This is what makes cave ecosystems so fragile and so precious. The creatures inside them evolved in isolation, cut off from the surface world for thousands or even millions of years. They are living records of ancient lineages. Some cave species are more closely related to animals found on distant continents than to anything living nearby on the surface. The caves preserved them, kept them safe from competition and change, while the world above shifted and transformed. The darkness that seems so empty holds something irreplaceable. A pale fish drifts through cold water. A white salamander waits on a stone. The cave breathes slowly around them, and life, in its quiet and patient way, continues. Beneath the surface of the ocean, the same slow dissolving is happening. The same patient chemistry that carves caves beneath Texas and Florida works just as quietly under the sea. Limestone does not stop at the shoreline. It extends outward beneath shallow coastal waters, beneath the continental shelves, beneath places where sunlight barely reaches, and where limestone meets water, dissolution follows. Some of the most remarkable sinkholes on Earth are not on land at all. They sit on the ocean floor, filled with seawater, hidden from view. Scientists call them submarine sinkholes, and they share the same origins as the ones we find on dry ground. They formed during ice ages when sea levels dropped dramatically and vast stretches of the seafloor were exposed to open air. Rain fell on that bare limestone, sinkholes opened. And then, as the ice melted and the seas rose again, the ocean swallowed them whole. This happened slowly. Over thousands of years, the water crept back across the land. It filled the valleys and the plains. It covered the forests and the river mouths. And it filled the sinkholes too, one by one, until they became part of the seafloor. What was once a hole in dry rock became a hole in the ocean bottom. The shape remained. The depth remained. Only the air was gone, replaced by salt water. Scientists have found these submarine sinkholes in the waters off Florida, in the Gulf of Mexico, in the Adriatic Sea, and along the coasts of Australia. Some are small, just a few meters across. Others are enormous. The Dragon Hole in the South China Sea is the deepest known underwater sinkhole on Earth. It plunges more than 300 meters straight down from the seafloor. That is deeper than the Eiffel Tower is tall. Its walls drop away into a darkness that sunlight never touches. The Dragon Hole is so deep and so still that the water inside it behaves differently from the ocean around it. Near the surface of the hole, where some light still filters down, marine life is abundant. Fish and corals and sea creatures of many kinds gather there. But deeper down, the water grows still and oxygen poor. Very little can survive in those lower depths. The hole becomes a kind of boundary, a place where the living world fades into something much older and much quieter. What makes submarine sinkholes so fascinating to scientists is what they preserve, because the water inside them is often isolated from the currents and mixing of the open ocean. Sediment settles there undisturbed. Layers of silt and organic material build up over centuries, over millennia. Those layers are like pages in a book. Each one holds a record of what the climate was like, what creatures lived nearby, what the ocean chemistry looked like at that moment in time. Scientists can drill into those sediments and read the past. Some submarine sinkholes also hold something unexpected: fresh water. Groundwater from inland aquifers, those vast underground reservoirs of fresh water, sometimes flows outward through limestone passages and emerges on the seafloor. Where this happens, fresh water bubbles up through the salt water around it. two liquids mix slowly at the edges, but resist full blending at first, because fresh water is lighter than salt water. Divers who swim near these submarine springs describe a shimmering, wavering effect at the boundary between the two, like looking through imperfect glass. The fresh water rises in pale, ghostly columns before dissolving into the sea. These submarine springs are called ankyline systems when they connect to both the ocean and inland groundwater. The word ankyline comes from a Greek phrase meaning near the sea. These systems are rare and strange. They are neither fully marine nor fully freshwater. They exist in between, in a zone where two worlds overlap. And like the dark caves above them, they shelter creatures found nowhere else. Tiny shrimp, blind and colorless, drift through the passages. Microscopic organisms cling to the walls. Life finds its way into every available space, no matter how unlikely. The ocean floor, then, is not a flat and featureless plain. It has its own caves, its own sinkholes, its own hidden rooms. The same forces that shaped the land beneath our feet shaped the ground beneath the sea. Rainwater and time, and the quiet patience of chemistry worked there too, long before the ocean returned to cover their work. The seafloor holds those old shapes still, waiting in the dark water. A pale column of fresh water rises through the salt. A blind shrimp drifts through an ancient passage, and the ocean, vast and slow, keeps its secrets with great care. For most of human history, karst landscapes were a mystery without a name. People who lived above them knew something strange was happening. Fields would crack open. Streams would vanish. The ground would groan and give way. But no one had a full picture of what was happening beneath their feet. That picture came slowly, built by many hands over many centuries. The word karst itself comes from a region in what is now Slovenia, along the Adriatic coast. That rocky plateau, called the Kras in Slovenian, puzzled early European travelers. The land was dry on the surface, even though rain fell regularly. Rivers appeared and disappeared without explanation. The soil was thin and pale, stretched over bare gray limestone. In the 1600s and 1700s, European scientists began visiting this region to study it. understand why the ground behaved so differently here than anywhere else they knew. One of the first serious studies came from a Slovenian scholar named Johann Weikart von Valvasser. In 1689, he wrote a detailed account of a lake near the town of Cerknica. The lake would fill with water each spring, then drain completely by summer. Von Valvasser correctly guessed that underground passages were responsible. He described a hidden network of tunnels carrying water in and out of the basin. His peers in the Royal Society of London found his explanation convincing. It was one of the first times someone described karst drainage in print with any scientific care. Over the next 2 centuries, geologists across Europe began mapping karst regions by walking them. They lowered ropes into sinkholes. They followed rivers into cave mouths. They measured the chemistry of spring water and compared it to rainfall. Slowly, they built a theory. Limestone dissolved in weak acid. Water moved underground through cracks and tunnels. The surface above was shaped by what happened below. By the late 1800s, the word karst had entered the scientific vocabulary as a formal term for this kind of landscape. But walking a landscape only reveals so much. The real breakthrough came from above. In the early 20th century, aerial photography changed everything. Pilots flying over karst regions in Europe, China, and the Caribbean sent back images that no ground explorer had ever seen. From the air, the patterns became clear. Hundreds of circular depressions, called dollines, dotted the land in clusters. Dry valleys curved through the rock with no rivers to explain them. Ridges and towers of limestone rose in rows, like the spines of buried creatures. From the ground, these features looked like ordinary hills and hollows. From the air, they told a completely different story. The tower karst of southern China was one of the most striking discoveries. Seen from above, the landscape looked almost impossible. Thousands of steep limestone pillars rose from flat green plains, each one separate, each one sharp. Geologists had visited the region for decades without fully grasping its scale. The aerial photographs made the scale undeniable. This was not a collection of hills. It was a single vast system shaped by millions of years of dissolution, stretching across thousands of square miles. Then came satellites, and the picture grew larger still. Beginning in the 1970s, satellite imagery allowed scientists to map karst landscapes across entire continents. They could see the great karst plateaus of the Yucatan Peninsula from orbit. They could trace the limestone belts of the Appalachians in a single glance. They could compare the density of sinkholes in one region to another, counting hundreds of depressions in the time it would have taken a field geologist months to survey on foot. Modern satellites carry instruments that go far beyond ordinary cameras. Radar systems can detect subtle changes in ground elevation, measuring the slow sag of land above a dissolving cave system. Some satellites measure tiny shifts in Earth's gravitational field, and those shifts can reveal underground voids where rock has been removed by water. A hollow space beneath the surface has slightly less mass than solid rock. Gravity sensors can feel that difference from space. Scientists used these tools to map karst regions in places that had never been studied closely before. Large karst systems were identified beneath the sands of the Sahara, remnants of a wetter climate thousands of years ago. Karst features were found beneath the ice of Greenland, carved by ancient rivers before the glaciers arrived. The planet, seen from orbit, revealed itself to be far more hollow than anyone had imagined. What began with a puzzled traveler staring at a disappearing lake in Slovenia grew, over 3 centuries, into a science that reads the bones of the Earth from space. The tools changed, the scale changed, but the question stayed the same. What is happening beneath our feet? Karst country covers more of this planet than most people ever guess. Roughly 15 to 20% of Earth's dry land surface sits on soluble rock. That means nearly 1 in 5 square miles of land on Earth is shaped, at least in part, by the slow work of dissolving stone. And yet, most people walk through their entire lives without ever thinking about what lies beneath them. The ground feels solid. It feels permanent. But in karst country, permanence is always a question. The largest karst region on Earth stretches across southern China. The Guangxi and Guizhou provinces hold some of the most dramatic limestone scenery anywhere on the planet. Tall, narrow towers of rock rise straight up from flat valley floors, like stone pillars holding up the sky. These formations are called tower karst, and they form when water dissolves the rock around them over millions of years, leaving behind only the hardest, most resistant columns. Some of these towers stand 300 meters tall. Walking among them feels like moving through a forest made of stone. What surprises many people is that this landscape is not ancient by geological standards. The limestone itself is old, formed from the shells of sea creatures that lived hundreds of millions of years ago. But the towers, the caves, and the sinkholes that shape this region were carved mostly within the last few million years. Geologically speaking, that is recent. The land you see in southern China today is a young face on very old bones. Southeast Asia holds another surprise. The islands of Malaysia, Indonesia, and the Philippines contain some of the world's largest cave chambers, carved inside karst hills that rise from dense rainforest. Sarawak Chamber, inside Gunung Mulu National Park in Malaysia, is the largest known cave chamber on Earth by area. It could hold 40 Boeing 747 aircraft inside it, with room to spare. The chamber is so large that its far wall disappears into darkness, even when you stand at the entrance with a powerful light. The air inside is cool and still, and the silence is the kind that feels like weight. The Yucatan Peninsula in Mexico is another place where karst rewrites expectations. The entire peninsula sits on a flat sheet of limestone with almost no surface rivers at all. Rain falls, soaks into the ground, and vanishes. The water travels through a vast underground network before reaching the sea. Scientists believe this underground system is one of the longest flooded cave networks on Earth, stretching for hundreds of kilometers beneath the jungle floor. The surface looks ordinary, even unremarkable, but below it runs a hidden river system larger than many above-ground rivers in the world. Europe holds its own surprises. The Dinaric Alps, running along the coast of the Adriatic Sea through Slovenia, Croatia, and Bosnia contain some of the densest karst terrain on the planet. This is the region that gave karst its name, and it remains one of the most studied karst landscapes in science. But even here, after 3 centuries of research, new caves and new passages are still being found. The rock gives up its secrets slowly. Perhaps the most counterintuitive karst region of all lies beneath the ice of Antarctica. Evidence suggests that large areas of bedrock beneath the Antarctic ice sheet are made of soluble limestone. Liquid water, warmed by geothermal heat from below, pools at the base of the ice. That water can dissolve rock. Scientists believe karst processes may be actively shaping the bedrock beneath one of the coldest places on Earth. Right now, in complete darkness, under kilometers of ice, the idea that a warm, wet, dissolving process could be happening beneath a frozen continent seems impossible. But the chemistry does not care about the temperature above it. It only cares about the water and the rock. What all these regions share is the same quiet logic. Water finds weakness. Weakness becomes a crack becomes a passage becomes a cave becomes a void, and the surface above, cut off from the support it once had, eventually comes to terms with what has been taken away. This process plays out on every continent, in every climate, in jungles and deserts, and beneath polar ice. The rock type changes, the speed changes, the scale changes, but the process is always the same patient negotiation between moving water and dissolving stone. The world is far more hollow than it looks, and the hollow places, it turns out, are everywhere. Nowhere does that quiet logic feel more alive than in the Yucatan Peninsula of Mexico. Here, the limestone shelf that forms the floor of the land is riddled with passages and chambers. And where the roof of a chamber has fallen in, the sky opens up and water fills the space below. These flooded sinkholes are called cenotes, from a Mayan word meaning sacred well. They are windows cut straight through the earth, and they have been drawing people to their edges for thousands of years. The water inside a cenote is something you have to see to believe. It is not murky or dark. It is clear in a way that feels almost unreal. A deep blue-green that shifts to turquoise near the surface and fades to black far below. Sunlight pours in through the open ceiling and scatters through the water in long, pale shafts. The walls are pale limestone, draped in hanging roots from the trees above. It looks like a room that the earth made by accident and then filled with light. The Maya did not think of cenotes as accidents. They believed these pools were sacred places, direct passages to Xibalba, the underworld where their gods lived. Cenotes were used for ritual offerings, for ceremonies, and as the primary source of fresh water across a peninsula that has almost no rivers at all. The Yucatan is so porous, so full of underground channels, that rainwater simply vanishes into the ground before it can form a surface stream. The cenotes were not just holy. They were essential to life, and the cenotes are all connected. Beneath the Yucatan, a vast network of flooded tunnels links hundreds of these open pools into one enormous underground river system. Divers have been mapping these passages for decades. The Sac-Acton system, discovered and explored over many years, is currently the longest known underwater cave system in the world, stretching more than 370 kilometers. It is not a single cave. It is a branching, looping web of flooded passages, and it connects directly to the sea. That connection to the sea is where the story opens up into something larger. The water inside the cenotes is not all the same. Near the surface, the water is fresh, fed by rain that has filtered down through the limestone. But deeper down, below a certain depth, the water becomes salty. Seawater has pushed inland through the porous rock, and it sits beneath the fresh water in a distinct layer. The line where fresh water meets salt water is called the halocline, and divers who pass through it describe a strange visual shimmer, like swimming through a slow, gentle wave that never breaks. This mixing of fresh and salt water creates a chemical environment unlike almost anywhere else on Earth. The place where the two waters meet is rich in minerals, and it supports a thin, hazy layer of microbial life, tiny living organisms that feed on the chemistry of that boundary. Scientists studying these microbes believe they may be similar to life forms that existed on Earth billions of years ago, before before oxygen filled the atmosphere. The cenote, in this way, is not just a window to the underworld. It is a window to deep time. The cenotes also carry the memory of a very different world. During the last ice age, sea levels were much lower than they are today. The Yucatan's underground passages were not flooded then. They were dry caves, full of air, and ancient humans walked through them. Archaeologists have found human bones and the remains of giant animals, including giant sloths and saber-toothed cats, deep inside these passages. When the Ice Age ended and sea levels rose, the caves flooded, and everything inside them was preserved in cold, still water for thousands of years. One of the most remarkable finds came in 2007, when divers discovered the nearly complete skeleton of a teenage girl in a flooded chamber deep in the Yucatan system. She was named Nea. Her bones were more than 12,000 years old. The water had kept her safe all that time, sealed in darkness, while the world above her changed beyond recognition. The cenotes hold all of this at once. They are a water source and a sacred site. They are a habitat for ancient microbes and a tomb for Ice Age animals. They are connected to the sea, to the rain, to the roots of the trees above, and to the great limestone shelf that the whole peninsula rests upon. Every drop of rain that falls on the Yucatan eventually finds its way into this system. Every cenote is part of the same slow, patient flow. The water moves through the rock, through the dark, through the centuries, and it surfaces here in these open pools of impossible blue, still and quiet, and full of everything the earth has kept. Far out in the open ocean, in places where the seafloor drops away into darkness, there are circles of deep blue water surrounded by shallow turquoise seas. They look like bruises on the surface of the ocean. They look like holes punched through the floor of the world. These are blue holes, and they are, in every sense that matters, sinkholes. They are the same ancient process, the same slow dissolving of limestone, the same patient work of water on rock. The only difference is where they formed and when. Blue holes began the same way the cenotes of the Yucatan did. During the last ice age, sea levels dropped dramatically, sometimes by more than 300 100 feet below where they sit today. Vast stretches of seafloor were exposed to open air. Rain fell on those limestone shelves. The same weak acid that carved the caves of Kentucky and the karst towers of southern China went to work on the exposed rock. Caves formed, chambers opened. The ground hollowed out from below, slowly and silently, over thousands and thousands of years. Then the ice melted. The seas rose. The coastlines moved inward, swallowing those ancient landscapes whole. The caves flooded. The sinkholes filled with seawater. And what had once been dry karst country became the seafloor, with these great circular openings still visible from above, dark against the pale sandy bottom. The most famous blue hole on Earth sits off the coast of Belize in the Caribbean Sea. It is called the Great Blue Hole, and it is nearly 1,000 feet across and more than 400 feet deep. From the air, it is a perfect circle of deep indigo blue, ringed by a reef of pale coral. Jacques Cousteau, the French ocean explorer, visited it in 1971 and declared it one of the finest diving sites in the world. That attention helped make it famous. In 1996, it was named part of the Belize Barrier Reef Reserve System, a UNESCO World Heritage Site, meaning the world recognized it as something worth protecting. Inside the Great Blue Hole, divers find something unexpected. The walls are lined with stalactites, those hanging stone formations that only grow in dry caves in open air. Some of these stalactites are tilted at odd angles. Scientists believe this happened during a time when the cave itself shifted, possibly during a partial collapse, before the sea came in and froze everything in place. The stalactites are a record of a world that no longer exists above the waterline. They are proof that this place was once dry, once open to the sky, once part of a living karst system breathing in the rain. The water inside a blue hole behaves differently from the ocean around it. Below a certain depth, the water stops moving. There is almost no oxygen down there. There is very little life, but that stillness is exactly what makes blue holes so valuable to scientists. Sediment, the fine particles that drift down through the water, settles in these still depths in perfect layers, one year on top of the next, undisturbed for thousands of years. Scientists read those layers the way they read tree rings. Each layer tells a story. Hurricane seasons leave a distinct mark. Droughts leave another. The record goes back further than almost any other natural archive in the Caribbean. A team of researchers studying the Great Blue Hole's sediment layers published findings in 2019 suggesting that drought, made worse by a changing climate, played a role in the decline of the ancient Maya civilization. The Blue Hole held that answer in its quiet, still depths, waiting for someone to come and read it. Blue holes exist in many places around the world. The Red Sea has them. The South China Sea has them. The Bahamas have dozens, some offshore and some on land, where the rock collapsed and the sea rushed in. Each one is a window into a different moment of Earth's past, a different chapter of the same long story of water and stone and time. What is remarkable is how much these places have changed and how much they have stayed the same. The process that made them is billions of years old. The chemistry of rainwater dissolving limestone has not changed since the first carbonic acid fell on the first exposed rock. But the world around these formations has shifted enormously. Sea levels have risen and fallen. Ice sheets have advanced and retreated. Coastlines have moved. Civilizations have risen on the karst above, drawn water from it, built cities on it, and sometimes vanished, while the blue holes below kept their slow, patient record of everything that passed. The ocean covers the old caves. The old caves keep the ocean's secrets, and the water, always the water, connects them all. Civilizations have always been drawn to karst country. The ground is fertile. The water is close. The stone is soft enough to carve and build with. And so, over thousands of years, people built their towns and cities right on top of the hidden world below. They did not know what was underneath. They could not see it. And for a long time, the ground held. But cities are heavy. A single city block, with its buildings and roads and buried pipes, and the constant weight of people and vehicles moving across it, presses down on the earth with enormous force. That pressure, combined with the slow, patient work of water dissolving the rock below, can push a karst landscape toward its limit. The caves and voids that took thousands of years to form do not always wait for a convenient moment to give way. Urban sinkholes are different from the ones that open in quiet forests or empty fields. When a sinkhole opens in a city, it opens beneath pavement, beneath pipes, beneath foundations. The collapse happens fast, and the signs are often hidden. A road might look perfectly solid on the surface, while the rock beneath it has been hollowing out for decades. The asphalt holds its shape even as the support beneath it disappears. Then, one morning, a car drives over the wrong spot, and the ground simply opens. Guatemala City has seen some of the most dramatic urban sinkholes ever recorded. In 2010, a sinkhole opened in the middle of the city that was roughly 60 feet wide and more than 60 feet deep. It swallowed a 3-story building hole. The walls of the hole were nearly vertical, smooth and sharp, dropping straight down into darkness. Investigators found that the city's aging sewer and drainage systems had been leaking for years, sending water into the volcanic rock and loose soil below. The water did what water always does. It found the weak places and wore them away. This is where light becomes part of the story. When a sinkhole opens in a city, the first thing people notice is the sudden appearance of darkness in a place that was bright. A hole in a road lets in daylight where there was none before. Engineers lower cameras and lights into the void, and for the first time, the hidden space below a city becomes visible. The beams of those lights reveal something strange and unsettling. The underside of the city itself. Pipes hanging in midair. Roots of trees dangling into empty space. The bottoms of foundations with nothing beneath them. Ground-penetrating radar, a tool that sends radio waves down into the earth and reads what bounces back. Let scientists see these voids before they collapse. The radar image shows the difference between solid rock and empty space as clearly as light shows the difference between shadow and open air. Cities in karst regions now use this technology to scan their streets, looking for the dark patches in the radar image that mean trouble is forming below. Some cities sit almost entirely on karst. San Antonio, Texas, is built over the Edwards Aquifer, a vast underground water system held inside limestone. The city draws its drinking water from that aquifer. It also sits above the caves and voids that the same water carved out over millions of years. Engineers there monitor the ground constantly, watching for the small signs that precede a collapse. Tiny cracks in pavement, slight depressions in the road surface, the faint settling of a building's foundation. Madrid in Spain has dealt with sinkholes caused by ancient gypsum deposits dissolving beneath the city. Gypsum, a soft mineral that dissolves even faster than limestone, can create voids quickly by geological standards. Streets in parts of Madrid have dropped and cracked as the gypsum below slowly disappeared into the groundwater. There is something quietly remarkable about this. The same process that carved the great cave systems of the world, that built the cenotes the Maya considered sacred, that formed the blue holes now resting on the ocean floor, is still happening right now. Beneath the streets where people walk to work each morning, the water does not know there is a city above it. It only knows the rock and the slow chemistry of dissolving what it touches. The light that floods into a new urban sinkhole is the same light that has never reached those depths before. It illuminates a space that formed in darkness over centuries without any witness. And for a brief moment, before the engineers arrive with their barriers and their cameras and their plans to fill it back in, the hidden world and the surface world look at each other directly. The city sees what is underneath it, and the darkness, for once, is lit. Humans have always changed the land around them, but in karst country, those changes reach deeper than most people realize. The ground here is already fragile. It is already hollow in places, already laced with voids and channels that took thousands of years to form. When humans arrive and begin pulling water from the earth, or piling weight onto the surface, or sending vibrations down through the soil, they do not create the process. They simply speed it up. The sound of that acceleration is not always dramatic. Sometimes it is a low creak, like old wood settling. Sometimes it is a sudden crack that travels up through a concrete floor and into the soles of someone's shoes, and and sometimes there is no sound at all, just a slow and silent sag in the earth that no one notices until the morning a car disappears into the street. Groundwater pumping is one of the most powerful forces humans use to trigger sinkholes. When people drill wells and draw water out of the ground, the water table drops. That water was doing something important. It was filling the spaces inside the rock, and that pressure helped support the weight of everything above it. When the water leaves, that support leaves with it. The soil and sediment above begin to settle into the voids below. In Florida, where karst limestone sits just beneath a thin skin of sandy soil, heavy pumping has caused sinkholes to open in neighborhoods, in parking lots, and beneath homes. The sound of a sinkhole forming in loose, saturated soil has been described by witnesses as a soft, wet tearing, almost like fabric giving way. Construction adds weight to ground that was never designed to carry it. A new building, a road, a parking structure, all of that mass presses down onto the surface. In karst terrain, that pressure can push through weakened rock and cause the thin ceiling of a hidden void to give way. The vibrations from heavy machinery, from pile drivers hammering foundations into the earth, can also shake loose the fragile arches of underground caves. Scientists have documented cases where construction work triggered cover collapse sinkholes within days of breaking ground. The machines send a deep, rhythmic thudding into the earth, and the earth, in some places, answers back. Leaking water pipes are another quiet culprit. A pipe buried beneath a street carries water under pressure. When that pipe develops a crack, water seeps out into the surrounding soil. Over months or years, that slow leak dissolves the rock below, or washes the fine particles of soil down into deeper cracks, leaving a growing void just beneath the pavement. The sound here is almost nothing at all, just the faint hiss of water finding its way through the dark. But the result can be sudden and total. Roads in cities across Europe and North America have collapsed without warning over leaking pipes, the pavement dropping into spaces that the escaping water carved in silence. Mining also plays a role. In parts of England, old salt mines were dissolved out of the rock, using a process called brine pumping, where water was injected into salt deposits to dissolve them, and then pumped back out. Salt dissolves even faster than gypsum, and gypsum dissolves faster than limestone. The result in some English towns was a landscape that slowly, steadily sank. Buildings tilted, roads buckled. The ground moved not with a crash, but with a long, grinding patience that took decades to fully show itself. Even the weight of water stored in reservoirs can trigger changes in karst below. The pressure of millions of tons of water pressing down on the earth can open fractures, push water into new pathways, and accelerate the dissolving of rock that had been stable for centuries. Engineers who build dams in karst regions must study the ground carefully before they begin, because a reservoir built over a hidden cave system can drain away through the rock, or worse, cause the ground beneath the dam itself to weaken. What all of these forces share is that they interact with something already in motion. The karst was dissolving before the city arrived. The voids were forming before the pipes were laid. Humans did not invent this process. They joined it, often without knowing it, and they turned up the speed. The earth beneath a modern city is not still. It is shifting, dissolving, settling, responding to every pump and pipe and passing truck. The low hum of a city at night travels down through the pavement, through the soil, through the rock, and into the dark chambers below. The ground listens, and sometimes, quietly, it moves. The ground listens, and scientists have learned to listen back. Over many decades, researchers who study karst have built a quiet science of warning. They watch for patterns. They measure small changes. They read the land the way a doctor reads a patient, looking for signs that something deeper is shifting. And what they have found is that the earth, before it gives way, almost always speaks first. One of the clearest warning signs is a crack in the soil, not the kind that forms in dry summer heat, but a crack that appears without explanation, running in a rough circle or arc across a lawn or a road. These cracks often follow the shape of the void below. As the ceiling of an underground chamber slowly sags, the surface above begins to stretch. The soil pulls apart in a ring, Scientists call this a tension crack, and its shape can tell them a great deal about the size and depth of what lies beneath. The mathematics here are elegant. The angle of the crack, measured against the depth of the void, follows a predictable ratio. A void that sits 30 feet below the surface will tend to produce surface cracks within a certain radius. A deeper void produces a wider ring. Engineers use these ratios to estimate how large a forming sinkhole might be before it ever opens. The geometry of collapse follows rules that repeat themselves. In limestone plains in Florida, in gypsum fields in Spain, in chalk downs in England. The same angles, the same ratios, the same quiet warning written in the dirt. Water is another messenger. When a sinkhole is forming, groundwater often begins to move in new directions. Wells that once produced steady, clear water may begin to run cloudy. The cloudiness comes from fine particles of soil being pulled downward into the growing void. Hydrologists, the scientists who study the movement of water, can measure the turbidity of a well, which is simply how cloudy or clear the water is, and track changes over time. A sudden rise in turbidity, with no rainfall to explain it, can signal that soil is migrating underground. The water is carrying the earth away, grain by grain, into the dark. Ground-penetrating radar has changed this science deeply. A technician can drive a vehicle slowly across a field or parking lot, and the radar sends pulses of energy downward into the soil. Those pulses bounce back differently depending on what they hit. Solid rock returns a clean, sharp signal. A void returns almost nothing, a hollow echo, a gap in the data. The resulting image looks something like a weather map, with layers of color showing different densities of material below. A trained eye can spot a forming void from these images before any crack appears at the surface. The radar sees what no shovel could reach. Satellites have added another layer of precision. Instruments aboard orbiting spacecraft can measure the elevation of the ground to within a few millimeters. When a section of Earth begins to subside, sinking slowly as material migrates below, the satellite detects the change. Scientists compare images taken weeks or months apart and look for areas where the surface has dropped, even slightly. A drop of just a few centimeters, invisible to the eye, can appear clearly in satellite data. This technique, called INSAR, which stands for Interferometric Synthetic Aperture Radar, has been used to detect sinkhole formation days before collapse in regions of Florida and the Dead Sea Basin. The Dead Sea offers one of the most dramatic examples on Earth. As the sea has shrunk over recent decades, the fresh water that once flowed beneath its shores has retreated. Salt layers that were once stable are now dissolving rapidly. Thousands of sinkholes have opened along the shoreline, some appearing overnight. Scientists monitoring the region with satellite data and ground sensors have built models that predict where new sinkholes are most likely to form next. The models are not perfect, but they are improving season by season as more data arrives. What all of these tools share is that they translate the hidden language of the Earth into numbers. A crack angle, a turbidity reading, a radar echo, a millimeter of subsidence. Each measurement is small on its own. Together, they form a picture of a process that has been running for millions of years, now watched by human eyes for the first time. The Earth has always been moving through these slow equations. We are only beginning to learn how to read them. And in learning to read them, we are learning something older and quieter than any city or road or reservoir. We are learning the pace at which the planet thinks. The tools scientists use to read that hidden language have grown remarkably precise. For most of human history, the only way to know what lay beneath the ground was to dig, or to wait for the ground to tell you itself, sometimes violently. Now, scientists carry instruments that can sense the shape of empty space without ever touching it. They can measure the pull of gravity from an aircraft. They can bounce radar waves through solid rock. They can listen to the way sound moves through stone and water and air. Each method reveals a different layer of the same quiet story. One of the most powerful tools is called ground-penetrating radar. It works much like the sonar a ship uses to map the ocean floor. But instead of sound moving through water, it sends radio waves down through soil and rock. those waves hit something different, a void, a water pocket, a layer of loose sediment, they bounce back. A receiver at the surface catches the returning signal. The time it takes to return tells scientists how deep the feature is. The shape of the signal tells them something about what it is. A trained eye can look at the readout and see the ghost of a cave that no human has ever entered. Gravity surveys work on a different principle entirely. Every material on Earth has mass. Mass creates gravity. A solid block of limestone pulls a sensitive instrument slightly harder than an empty cave does. Scientists carry instruments called gravimeters, which measure tiny changes in gravitational pull as they move across the ground, where the pull is slightly weaker than expected. Something hollow may lie below. The differences are incredibly small. We are talking about variations far too tiny for any person to feel, but modern gravimeters are sensitive enough to detect them, and the maps they produce can outline underground cavities with surprising accuracy. Seismic surveys add another layer of detail. Scientists generate small, controlled vibrations at the surface, sometimes with a mechanical hammer, sometimes with a small controlled charge. Those vibrations travel down through the earth and reflect off different layers of rock. Sensors on the surface record the returning waves. The pattern of reflections reveals the structure of the rock below, where it is solid, where it is fractured, where it thins out over an empty space. The same basic technique that oil companies use to find underground reservoirs can help geologists find the hidden rooms that sinkholes leave behind. From above, satellites continue to refine the picture. Instruments called interferometric synthetic aperture radar systems, often shortened to INSAR, can detect ground movement across wide areas with millimeter-level precision. They do this by comparing radar images taken at different times and measuring the tiny shifts between them. A patch of ground that has dropped by 2 millimeters since last month may not look different to the human eye, but to INSAR, it glows like a warning light. Scientists watching karst regions from orbit can sometimes see the slow, circular subsidence that signals a sinkhole forming weeks or months before it opens. What makes all of this so important is that karst landscapes hold an enormous amount of the world's fresh water. Scientists estimate that roughly a quarter of the Earth's population depends on groundwater that moves through karst rock. That water does not sit still in a single underground lake. It moves through cracks and channels and caves, sometimes traveling dozens of miles before it reaches a well or a spring. The same geology that creates sinkholes also creates the pathways that carry drinking water to millions of people. Mapping that system is not just a scientific curiosity, it is a practical necessity. When a new road is planned across karst country, engineers need to know where the voids are. When a city draws water from a karst aquifer, the word aquifer, meaning a body of rock that holds and carries groundwater, managers need to understand how that system connects and how fragile it might be. Pumping too much water too fast can lower the water table and remove the support that keeps the ground above from collapsing. The balance is genuinely delicate. Karst landscapes have been building for millions of years, dissolving and reshaping at a pace that matches deep geological time. Human activity can accelerate that process in decades. The tools scientists now carry into the field and into orbit are helping them understand where that balance sits and how close to the edge some of these systems already are. There is something quietly humbling about it. The ground beneath a quiet field or a busy street may hold a cathedral of empty space, carved by water and time, invisible and immense. Science is learning to see it, and in seeing it, to protect it. And yet, for all that science has learned, karst still holds its secrets close. Even with satellites overhead and sensors buried in the ground, there are questions that researchers have been asking for decades without a clean answer. That is not a failure. It is an invitation. The Earth is patient. It has been keeping these secrets for millions of years, and it will give them up slowly, on its own terms. One of the deepest open questions is this: how does water actually move through a karst aquifer? Scientists know the broad answer. Water flows through cracks and tunnels dissolved into the rock, but the exact path, the speed, the timing, the way one channel connects to another far away, is still poorly understood in most karst systems around the world. Researchers sometimes pour a harmless dye into a sinkhole and wait to see where it comes out. Sometimes it appears in a spring miles away. Sometimes it never appears at all. The water finds paths that no instrument has yet traced. This matters enormously. About a quarter of the world's population drinks water that comes from karst aquifers. That is roughly 2 billion people relying on a system that scientists still cannot fully map or predict. In the United States alone, karst aquifers supply drinking water to millions of people across Florida, Texas, Kentucky, Missouri, and many other states. The Floridan aquifer, one of the most productive in the world, sits beneath a thick layer of limestone and feeds springs, rivers, and city water systems across the southeastern United States. It is ancient, vast, and still not completely understood. What makes karst water so hard to study is its speed. In a sandy aquifer, water moves slowly, filtering through tiny grains of sediment over months or years. That slow movement cleans the water naturally. In karst, water can travel miles in hours, rushing through open tunnels with almost nothing to filter it. A chemical spill on the surface can reach a drinking water well very quickly. Sometimes before anyone even knows there is a problem. Scientists are still working out how to predict those pathways before a spill happens, not after. There is also the question of what lives in the water. Deep karst aquifers are not empty. They hold ecosystems, tiny creatures adapted to total darkness, cold temperatures, and very little food. Many of these species have never been named. Biologists believe that karst groundwater systems around the world contain hundreds, possibly thousands, of species that science has not yet described. Some may hold clues to how life adapts to extreme conditions. Some may produce compounds useful in medicine. Most will never be found if the aquifers that hold them are contaminated or drained before anyone thinks to look. The timing of sinkhole formation is another puzzle that keeps researchers up at night. Scientists can identify areas at high risk. They can find voids with ground-penetrating radar, but predicting exactly when a cover collapse sinkhole will open is still beyond current science. The process can take years of slow, invisible erosion and then happen in seconds. There is no reliable way yet to say, this sinkhole will open on this day. That gap in knowledge has real consequences for the people who live and work above karst terrain. Climate change adds another layer of uncertainty. Karst systems are sensitive to rainfall patterns. More intense storms can push more water underground faster, widening tunnels and destabilizing the rock above. Longer droughts can lower the water table and remove the buoyancy that helps support overlying sediment. Researchers are only beginning to model what a warmer, more variable climate will do to karst systems that took millions of years to reach their current shape. The models are improving, but the answers are not yet clear. And then there is the deep karst, systems buried so far below the surface that no drill has reached them, no dye has traced them, no sensor has touched them. Evidence suggests these deep systems exist. Seismic data, meaning the study of how sound waves move through rock, hints at large voids far below what humans have ever explored. What those spaces look like, how old they are, whether water still moves through them. These are questions without answers. There is something genuinely wonderful about that. The Earth is not a solved problem. It is a living, shifting, dissolving, rebuilding system, and it still has rooms we have never entered. Every answered question opens a hallway to 3 more. Scientists who spend their lives studying karst will tell you the same thing. The more you learn, the larger the mystery seems to grow. Not smaller, larger, and that somehow feels exactly right. Karst does not stand still. It never has. The landscapes we see today, the sinkholes, the caves, the hidden rivers, are not finished things. They are moments, snapshots in a process that began long before humans existed and will continue long after we are gone. The rock beneath our feet is always in motion, always becoming something else, always moving toward a shape we will never live to see. Think about what 1,000,000 years means to limestone. 1,000,000 years is enough time for a shallow cave to grow into a cathedral. It is enough time for a small sinkhole to widen into a valley. It is enough time for an entire plateau to be lowered by dozens of feet, grain by grain, dissolved into groundwater and carried quietly to the sea. Geologists call this process denudation, which simply means the slow wearing away of land. In karst country, denudation happens faster than in most other places on Earth. The rock does not just erode from the surface, it dissolves from within. Over tens of millions of years, entire mountain ranges made of limestone can be reduced to low, rolling hills. Scientists have found evidence of ancient karst systems that are now buried deep underground, sealed off by younger rock layers laid down on top of them. These are called paleokarst, meaning old karst, and they are like fossils of landscapes. They tell us that the same slow dissolving process has happened again and again across Earth's long history, in different places, in different ages, under different skies. Some of the oldest known karst features on Earth formed more than 500 million years ago, during a time when the continents looked nothing like they do today. The land masses were arranged differently. The oceans were in different places, and yet the chemistry was the same. Rainwater absorbed carbon dioxide. It became slightly acidic. It touched limestone, and it began to dissolve. The same quiet process running across 500 million years of time. The continents are still moving. They move slowly, only a few centimeters each year, but over millions of years, that adds up to enormous distances. Scientists believe that in roughly 250 million years, the continents will have drifted close enough together to form a new supercontinent. Some researchers call this future landmass Pangea Ultima. When that happens, the collision of tectonic plates will push up new mountain ranges. Some of those mountains will be made of limestone and dolomite, the same carbonate rocks that form karst today, and the rain will fall on them, and the dissolving will begin again. The sun itself will change. In about 5 billion years, our sun will expand into what astronomers call a red giant, growing so large it may swallow the inner planets entirely. Long before that happens, Earth's surface will become far too hot to support liquid water. Without water, there is no karst. The rain will stop. The caves will stop growing. sinkholes will freeze in whatever shape they have reached by then. The great dissolving will end, but the rock will still be there, holding the shapes of all those ancient spaces inside it, like a memory carved in stone. That is a long way off. In the time between now and then, Karst will keep doing what it has always done. New caves will open, old ones will collapse. Sinkholes will form in places where people have never seen one before. Springs will shift. Rivers will find new paths underground. The slow, patient chemistry of water and rock will keep rewriting the ground beneath us, one dissolved grain at a time. There is something deeply calming about this. The earth does not rush. It does not need to. It has time that we cannot really imagine. Time measured not in years or centuries, but in epochs and eons. And through all of that time, the same simple forces keep working. Water falls, rock dissolves, space opens, life finds its way in. The system keeps going, keeps changing, keeps building new rooms in the dark. We are here for a small part of this. We get to watch a few centuries of it, maybe a few generations of change, if we are lucky enough to study a place closely. But the process stretches back before us and forward beyond us, enormous and unhurried, written in the language of stone and water. The ground beneath our feet is not solid in any final sense. It is a slow conversation between rain and rock. And that conversation has been going on for longer than we can hold in our minds. It will go on long after the last human eye has looked up at the sky. And yet, even with all of that deep time swirling beneath us, people have always chosen to live on Karst. They have built their homes above the hollow ground. They have farmed the thin soils between the sinkholes. They have drawn water from the springs and called this strange, pitted land their own. There is something worth pausing on here. The very ground that can swallow a road or a building is also some of the most beautiful land on earth. Karst country has a look unlike anything else. The hills rise in steep, rounded shapes, almost like green bubbles pressed up from below. In southern China, in a region called Guilin, these hills stand hundreds of meters tall, draped in mist and forest, their reflections shimmering in the slow rivers below. Painters have tried to capture this view for over 1,000 years. Poets have written about it. Travelers have walked days just to stand at the edge of the Lee River and look at those impossible shapes rising from the flat valley floor. The rock beneath all of it is limestone, carved by millions of years of rain. In Slovenia, a small country in Central Europe, the word karst itself was born. The Kras Plateau there, a stony, wind-swept plain above the Adriatic Sea, gave scientists the name they now use for this entire type of landscape. The people of the Kras have farmed that rocky ground for centuries. They built stone walls by hand, clearing the fields one rock at a time, stacking the limestone into long, pale lines that still cross the hillsides today. The soil between those walls is thin and red, colored by iron minerals left behind after the limestone dissolved away. It grows grapes. The wine from that red karst soil has a flavor that people say you cannot find anywhere else on Earth. In the Yucatan Peninsula of Mexico, the Maya built one of the great civilizations of the ancient world directly above a karst plain. There are almost no rivers on the surface there. The rain falls and disappears into the rock almost immediately. The Maya survived because of the cenotes, those circular pools that open down into the flooded cave system below. Every city, every temple, every farm was placed near a cenote. The water that fed their civilization came entirely from underground. The karst was not just the ground they lived on. It was the reason they could live there at all. Across the world in Vietnam, Ha Long Bay holds nearly 2,000 limestone islands rising straight out of the sea. Some are hollow. Some have caves inside large enough to hold entire fishing villages. The water around them is green and still in the early morning, and the islands cast long shadows across the surface. This is karst that the ocean has claimed. The same slow dissolving process that makes sinkholes on land. But here, the sea has done the carving, eating into the bases of the stone towers over thousands of years. Even the plants that grow on karst are shaped by the rock. Limestone drains water quickly, so the surface is often dry even after heavy rain. The plants that survive there have learned to hold water tightly, to send roots deep into cracks in the rock, to grow karst hillsides, their roots wrapped around boulders, drawing minerals directly from the stone. The rock feeds the plant. The plant, when it dies, produces acids that slowly feed back into the rock. Even here at the surface, the conversation between life and limestone keeps going. The calcium in that limestone was once part of living things. Ancient sea creatures built their shells from it, layer by layer, over hundreds of millions of years. When they died, they sank. The shells piled up. The weight of time pressed them into rock. Now that rock dissolves in rain, and the calcium flows into rivers, into the sea, and into the bodies of new living things. The same atoms cycle through shell and stone and water and bone, over and over, across time so vast it has no edge we can see. We are part of this. The calcium in our own bones came from rock like this, dissolved and carried through water and food, and the long chain of living things that connects us to the ancient sea floor. When we stand on a karst hillside and look out at those strange, beautiful shapes, we are not just looking at the landscape. We are looking at something we are made of, something that is still moving through us, still cycling, still part of the same slow and patient process that has been shaping this world since long before the first eye opened to see it. And so the ground beneath us breathes, not in the way we breathe, with lungs and rhythm and effort, but it breathes in its own slow way. Water seeps down, rock dissolves, spaces open, caves grow, springs rise. Rivers run underground for miles and then spill back into the light. The whole system moves quietly in the dark without pause. This is what karst country really is. It is not just a type of land. It is a living process. It has been running since the first rains fell on the first limestone, hundreds of millions of years ago. It will keep running long after every city we have ever built has crumbled back into dust. There is something deeply calming about that. Think about what we have seen in this long, quiet night together. We have looked at the way a single raindrop picks up a tiny breath of carbon dioxide from the air and becomes just acidic enough to eat through solid rock. We have watched in our minds as that work goes on for 10,000 years, for 1,000,000 years, for longer than our imaginations can comfortably hold. we have seen the cracks widen into tunnels. The tunnels open into rooms. The rooms fill with the slow drip of mineral-rich water that builds columns of stone, one thin layer at a time. We have stood at the edge of the great blue hole in the ocean and looked down into water so deep and dark. It looks like the sea is keeping a secret. We have walked through the cenotes of the Yucatan, where the Maya once looked into the still, clear water and saw a doorway to another world. They were not wrong to feel that way. There is something genuinely other about those places. The light falls in from above, and the water glows a color that has no exact name. Somewhere between blue and green, and the memory of both. We have learned that the ground under our feet is not solid in the way we imagine. Beneath cities, beneath farms, beneath forests and deserts, karst rock holds water in its hidden chambers. Aquifers, those vast underground stores of fresh water, sit inside the same limestone that sinkholes are born from. The water we drink in many parts of the world has traveled through the dark for years before it reaches us. It has been filtered by stone. It has moved through passages no human eye has ever seen, and we have learned that this system is fragile. Pump too much water out, and the rock above can lose its support and fall. Pour pollutants into the ground, and they can travel through karst faster than almost any other rock type, moving from a farm field to a drinking well in days rather than decades. The same openness that makes karst so full of wonder also makes it easy to harm. But tonight, let the harm rest. Let the worry rest. Right now, somewhere in the Dinaric Alps of Europe, a river is vanishing into the ground through a hole in a hillside, and another river is rising from the earth a few miles away, and they are the same river. Right now, in the caves of Borneo, millions of bats are hanging in the dark, breathing slowly, waiting for night. Right now, in a flooded cave system in Mexico, a blind fish is moving through water that has not seen sunlight in 10,000 years, perfectly at home in the dark. The planet is doing what it has always done. It is cycling. It is dissolving and rebuilding. It is taking the old and making it new. The calcium that was once a shell on the floor of a warm ancient sea is moving right now, through water, through soil, through the roots of a tree, towards something it will become next. We are part of that movement. We have always been part of it. We did not arrive on this planet as strangers. We grew out of it, the way a stalactite grows from the ceiling of a cave, slowly, patiently, built from what was already here. And now the facts are done. The caves are quiet. The underground rivers run in the dark without needing us to watch them. The sinkholes sleep. The limestone waits. You can rest now too. The ground holds you. The planet turns beneath you, patient and old and full of hidden rooms. The stars are out. The karst hills are silver under the moon. Somewhere deep below, water moves through stone, and the world keeps its slow and ancient work. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet